Here we're looking at the inside of a nice looking sunroom. It's surrounded by glass and you can see the beautiful scenery outside. It must be a nice warm sunny day. The reason why we can see through the glass is because glass is transparent. Transparent materials allow light to pass through in straight lines. Some common examples of transparent materials are obviously glass, water, and air. Not all glass, however, is transparent. In this image, we're looking at glass, but we can't see through the glass, so obviously light is not being allowed to pass through directly. This type of glass is opaque. Opaque materials absorb light without re-emitting it, so light is not allowed to pass straight through. Common examples of opaque materials are most everything around you. Do me a favor, just look at the room around you and you'll notice that you can't see through most objects. So that means most objects are opaque. They're absorbing all the light that's entering them without letting it pass directly through. So here's those two terms together. Again, transparent is materials that allow light to pass through in straight lines, and opaque is materials that absorb light without re-emitting it. The thing I want to focus on is why. Why are some materials transparent and others opaque? The answer lies in a concept known as natural or resonant frequency. And that's the frequency at which an object will vibrate or oscillate when given energy. The cartoons I'm showing here are commonly used examples of resonance or resonant frequency. This top one is a tuning fork. If you've never seen one of these, I'll show you an example in just a minute. This is just a metal object that when struck will vibrate and create a sound of a very specific frequency. The frequency of sound that you hear, or the pitch, matches the frequency at which the metal itself is vibrating. It's shaking at that frequency. The frequency is very specific to the construction of the fork. So if you have a different fork of different mass or different physical construction, when struck, it will resonate or vibrate with a different frequency than the other tuning fork with the different physical construction. So that's an example of what we're saying. That's the natural frequency that the tuning fork wants to oscillate at when you give it energy by hitting it. The child on a swing shows a similar characteristic. If you've ever tried to push somebody on a swing, you'll know that there's a natural timing to your push if you want to get the most amplitude of swing. So if you want them to swing the highest. If you try to push at a timing that doesn't match the natural timing of the swing, it just doesn't produce much effect for the person. If you've never tried this, there's a lot of parks in the world. Just try it next time you're at a swing and pay attention. The timing is related to the frequency. So if we say it has a natural frequency, it's also true to say it has a natural timing. In my personal opinion, it's much easier to understand this concept with a visual component. If I can see it, it helps me understand it a little bit better. So to help with that, I found a couple of YouTube videos that do a decent job of demonstrating. The first one's going to involve tuning forks. Okay, so I talked about how when you strike a tuning fork, it creates a very distinct frequency or pitch, and that's based on the natural frequency of the tuning fork. That's the frequency the fork wants to vibrate at when you give it energy. And that's what we just heard here. I need to explain what he's doing here. This tuning fork on the left is identical to the tuning fork on the right. The reason why the tuning forks are in these boxes is because that allows the sound to be amplified underneath here. So it's much louder than it would be by itself. He's oriented this way so that when the tuning fork on the right oscillates the air and causes the sound, it'll go directly over into this box on the left. So that oscillating air will now be exposed to this tuning fork on the left, which is identical to the one on the right. Identical means that this one on the left has the same natural frequency as this one on the right, so it wants to vibrate at that same frequency. So let's watch what happens. So even though the tuning fork on the left wasn't struck, it is now oscillating, it's vibrating and creating that same pitch. And this has to do with resonance. The tuning fork wanted to vibrate at that frequency anyway, so there was a large reaction because of the air that it was in contact with vibrating at the frequency it wanted to vibrate with. When he attaches this extra clip, that changes the physical composition of the tuning fork, so it changes its natural frequency. This tuning fork no longer has the same natural frequency as the one on the right. So watch what happens this time when air from the tuning fork on the right is exposed to the tuning fork on the left. As you can see, there was no reaction by the tuning fork, even though the vibration coming from the tuning fork on the right was the exact same as the previous situation. So this is what I mean by resonance. An object will react very little if it's driven by a frequency that doesn't match its natural frequency. So there's just no reaction by the tuning fork on the left now that it has a different natural frequency. This is known as sympathetic vibration when they have the same natural frequency, and an oscillation in one creates an oscillation in the other. That's what I mean by sympathetic. That only happens when they have the same properties. In the second video I want to watch, the focus is about breaking a wine glass with just your voice. If you sing at a certain pitch, that can actually affect the wine glass in such a way that it will actually cause it to break. You may have heard that or seen something like that. So that's the focus on this one, and we're actually going to watch for a couple minutes. She does a really good job of explaining this entire concept.
Safety goggles, and don't try this at home. The reason this is so challenging is that the note that you have to hold has to be the glass's exact resonant frequency. We'll get to resonant frequency, but first we need to think of the glass not as something that you drink out of, but as an oscillating system. An oscillating system is a system that goes back and forth, like a playground swing. I know that back and forth is a vague definition, but there are too many different types of oscillating systems to get more specific than that. Electrically and magnetically oscillating systems, economically oscillating systems, like an economy that goes up and down, yeah. But mechanically, these are all oscillating systems. So when you flick a wine glass, it vibrates back and forth, pushing the air, and that's what makes the ringing note that you hear. Now back to the playground swing. The swing is a totally overused analogy for explaining resonance, but it's just so good. It's an oscillating system and it has a resonant frequency. You can describe resonant frequency two ways. One is that it's the frequency your swing will keep swinging at if you just let it go. In the wine glass, that frequency is the note it vibrates at if you flick it and let it ring. By the way, musical notes can always be described by their frequency or frequencies. Now, another way of describing resonant frequency is that if you drive your oscillating system at that frequency, it will have the maximum response in amplitude, meaning it'll have the maximum response in distance between the back and forth. So if you push the swing at just the right moment, or in other words, you match its resonant frequency, the amplitude will increase. I know you've done this, and it'll increase more than if you pushed it at any other frequency. Now, the wine glass analog is that if you sing at the glass at its resonant frequency, your vocal cords are vibrating the air molecules that vibrate the glass and drive it at its resonant frequency. And then just like the swing will go higher and higher, the glass will vibrate or shake harder and harder. And if you shake something hard enough, it will eventually break. So that's why this is so tricky. You have to sing at the exact right frequency and hold it really loudly.
Okay, so this goes on for a little while longer. If you want to watch it, I put the link up here. I did actually want to jump to the end though. So her channel is known as Physics Girl. She actually does a great job of explaining many concepts in physics if you ever want to check out her stuff. So resonance is when the frequency of a driving force causes a drastic increase in amplitude in comparison to other frequencies that only produce minimal amplitude. She showed a graph like this in the video. It's actually quite useful if you can understand this graph. So the amplitude here is meaning the size. We talked about amplitude a little bit when we discussed waves. So it's the amount of vibration, if you want to think about the displacement of the object. So if you want to think of this line as the actual peak of a vibration, like this, the vibration's relatively low until you get close to the resonant frequency. And all of a sudden that vibration starts to get bigger and bigger and bigger, that amplitude. And then as you get away from the resonant frequency, it dies back down again. And then it just continues on flat on both left and right sides. So keep that in mind, that if you're driving something, you're causing it to vibrate or shake at a natural frequency or near it, you get a large reaction in terms of the displacement, the movement. But at other frequencies, it's relatively little. If you remember, my original point to this video was to discuss the differences between transparent and opaque objects. So how does this all tie into that? Well, to me, it makes sense how that works if you think of materials as just a combination of molecules that are bonded together. So here I'm showing a representation of a solid. So these blue spheres are each representing a single molecule, and then they're all connected through bonds, which are these brown connectors here. When light passes through a material, it's got to pass all the way through this maze and this jumble of molecules. It's unlikely that light is ever going to pass through without running into one of those molecules. So there's going to be some sort of interaction. So I want to consider that interaction as light passes through the material. So it goes from one side to the other. It's actually better to not think of light as a wave in this case. Now I know I've said light is a wave, and it is, but it turns out that you can also think of light as an individual particle, or really it's a packet of energy. So this packet of energy is known as a photon. Unfortunately, we're running out of time in the semester, and we really won't have an opportunity to discuss photons in more detail. For now, it'll have to be good enough for me to say that under certain situations, you can treat light as single packets of energy or single particles. So we're going to track this photon as it makes its way through this material. Now, as it shoots through, it's more than likely going to interact or collide with a molecule. When it does, it gets absorbed. That's why I had it disappear into this molecule. If that absorption did not cause resonance, if there's very little reaction by the molecule to the absorption of the photon, then almost immediately the molecule will re-emit the photon. It'll send it on its way in the same direction it had originally. So it's something like this. Of course, that photon will most likely interact with other molecules, and eventually it'll make its way through the entire material. This would be an example of a transparent material, where the photon was allowed to travel through in a straight line, more or less. That was our definition of transparent material. Light passes through without changing direction. In real life, when this happens, that absorption and re-emission of the photon through all the various molecules happens so fast that we would never perceive any difference. To us, the light just passed through and there was no difference. So from an outside perspective, that light seemed to slow down just ever so slightly inside the material. It's not that the light actually slowed down, it just that absorption and re-emission process took a little bit of time. So what we say then is that the average speed overall of light is slowed when passing through a material. Okay, I'm going to modify that original situation slightly. This time, let's assume that the photon has a frequency that's very similar to the natural frequency of all of these molecules. For some reason, I felt like making them similar in color would show that. If this has a frequency similar to the natural frequency, that should create a state of resonance. Remember that resonance results in a large amplitude reaction. So when the photon is absorbed, that energy is converted into a large reaction, motion-wise, for the molecule. So I imagine it might look something like this. You'll have to forgive the crude animations, kind of the best I could do under the circumstances, but I think it proves a point. So the absorbed energy from the photon has now caused resonance or a large amplitude reaction in the molecule. That physically means it's going to start shaking and moving around more. I know I didn't really show it in the picture here, but that molecule is still bonded to its neighbors. These bonds are still there. So the motion is not going to go unnoticed. That's going to spread out. It's going to start to shake the neighboring molecules, which means that that energy has now gone from the original photon into the kinetic energy, the motion energy of all these molecules. So that energy has been fully absorbed. So eventually, you're going to get a total system that's just shaking more. In other words, if they all shake more, they have more kinetic energy, which is what we define as temperature. So you've increased the temperature of the object. This is an example of an opaque material, where the photon was not allowed to pass through. That energy has actually been absorbed, and now it's converted into thermal energy. So I'm going to redefine transparent and opaque. Let's start with transparent. Now I'm going to define it as materials whose molecules do not resonate with the type of light passing through it. Very little light energy is absorbed by the material. That was our first example where the photon was absorbed, but it was almost immediately re-emitted, so that overall there was little effect to the photon. I'll now define opaque as materials whose molecules do resonate with the type of light trying to pass through. The light energy is absorbed by the material. That's why if you try to shine a flashlight onto a piece of wood, nothing comes out the other side. All of that energy was absorbed by the molecules of the wood. I want to go back to the sunroom I started with. This looks like a nice, comfortable place to hang out. So let's say somebody's just relaxing there for a few hours enjoying the nice summer day. If this person was to do the same thing just outside, we know that they would most likely get sunburned unless they took proper precaution. However, if they do this inside, they can sit there all day and not get a sunburn. You don't get sunburn behind glass. Well, glass is obviously transparent to visible light from the sun, but it's not that visible light that causes sunburns, it's ultraviolet light, or UV light. So the fact that we don't get sunburn behind glass suggests that glass is opaque to ultraviolet light. When the UV light from the sun hits the glass, all of that energy gets absorbed, and so none of that is re-emitted on the other side as ultraviolet light. Another way we could say this, now with our understanding of resonance, is that glass molecules have a resonant frequency that is similar to the frequency of UV light, but not visible light. As evidence of this, you've probably seen somebody with a sunburn pattern like this. So this person obviously spent too much time in the sun without any sunblock, and they must have had their glasses on the whole time, because nothing underneath those glasses is burned. That's evidence that the UV light was blocked by the glass. As another example of this gentleman is holding a pane of glass. That's why we can see him right now. The square that you see here, this rectangle, that's marking an area that's also being filmed with an infrared camera, an IR camera. So if I overlay that infrared image, it looks like this. You can see the shape, the outline of the glass. Notice that the glass has the same coloring as the background wall, which suggests that they have similar temperatures. We can no longer see the gentleman's face, which suggests that glass is opaque to infrared light. So all that infrared light coming off of his face is being absorbed by the glass. In fact, coming off of any part of him, it's all being absorbed by the glass. So the frequency of infrared light causes resonance within the glass molecules in a similar way that the UV light did. Well, this is great and all for infrared cameras, but there's a very real, very practical consequence of all this. I'm showing it right here. These cars are just sitting in a parking lot soaking up sun all day. So you might have seen or heard discussions like this, where it doesn't take very long for the interior of your car to heat up when it's just sitting in the sun. This figure suggests that in only 10 minutes, there's a difference between the outside temperature and the inside temperature of 19 degrees. After another 20 minutes, so 30 minutes total elapsed time, the temperatures climb to 114 degrees. Okay, so these can lead to serious situations if you're stuck inside of a car. The cause of all this is that glass is transparent to visible light. The UV light is blocked by the glass, of course, from entering, but the visible light can pass right through. The material or the upholstery inside your car is not transparent to visible light, it's opaque, so it absorbs all that visible light that falls on it. When it's absorbed, some of that energy gets spread around, which increases the temperature of the material. The increase in temperature now increases the amount of infrared light being re-emitted by the material. So that's kind of what's happening, is a lot of the visible light that entered was absorbed and then re-emitted as infrared light. Glass is opaque to infrared light, so the light is trapped. It's no longer allowed to leave the car. Plenty of energy can enter, but not nearly as much can leave, which is why the temperature increases so rapidly. So if you want your next trillion-dollar idea, invent glass that is transparent to both visible and infrared light. I guarantee you instant success. As one last demonstration, this is a slightly different situation, but similar effect. This gentleman has his hands inside of a black plastic bag. Okay, clearly this black plastic is opaque to visible light because we can't see what's inside. If we look at this same image with an infrared camera, you can clearly see the gentleman's hands. Okay, these are the same images. This is just a visible digital picture, and this is one from an infrared camera. The fact that I can clearly see all of his hands and fingers suggests that the black plastic is transparent to infrared light. So to me, this is just fascinating. The situations have flipped. Glass was transparent to visible light, but opaque to infrared. This black plastic is opaque to visible light, but transparent to infrared. So hopefully this is demonstrating how the different frequencies of light react differently with the molecular structure of different material. It causes resonance in some material and not in others. So different types of light will behave differently when passing through a material. And I think that gives us a good overview of transparent material versus opaque.